Ever since I left the city, you got a reputation for yourself now. Everybody knows and I feel.
Hello and welcome to the video on linear approximation and applications. So in life, there are a lot of times that we're interested in the effect of a small change. In this case, in this calculus class, we're going to denote our small change as delta x, which delta means change in, okay? So this is change in this case, the x value. So change in x value. So let's say we start off with our x value being x equals some number a, some constant a. And then we change it, so on a number line this would look pictorially like here's a, and then we're going to change it, we're going to move it by delta x, by some factor of change, okay? So once we do that, our new point is going to be a plus delta x, okay? So this is our old point and this is our new x point. So our new x point is going to be x equals a plus delta x, okay? So another way to rewrite this, just in terms of delta x, that's going to be x minus a, okay? So these two equations mean the same thing, all right? So this is what's happening to a. To x. This is what's happening to x on the x-axis. So what would happen to the function? Okay, so let's say we have some kind of function, f of x. Okay, so I'll write this on the next slide. So if we're changing x equals a to x equals a plus delta x, the effect on our function, and I'll denote our function with an f of x, is the following. So basically what we're going to do is evaluate that function at our new point, a plus delta x, and we're going to subtract away the value of the function at the old point, which is just a. Okay, so this will give us how much did our function change with response to the change in x. Okay, this is also denoted delta f, which stands for the change in the function value. Okay, all right. So what we can say from here is that if here's something kind of new. So if our function is differentiable, and at x equals a, so it has to be differentiable at this point, and here we go, and our delta x is small, okay, then we can say that f of a plus delta x minus f of a is equal to our change in f. So I just rewrote this line here, right? But here's the important part, is that this is about equal to, or approximately equal to, the first derivative of our function evaluated at a, and then times a delta x, okay? So this is the important part here, and I'll explain why on the next slide. So that relation basically comes from, or develops from, the tangent line or linear approximation, okay? So I'll just rewrite it here, the last line that I wrote on the last slide, on the previous slide. So this, and then that's equal to delta f, which is about equal to f prime of a times delta x. Okay, so let's say graphically, this is what we have. So we have our x and our y, and we have some curve going along, okay? So this is our f of x graph. Okay, so let's say we're looking at this point. This is point A on the x-axis, okay? And this, consequently, on the graph is our f of a, okay? That's what it is on the y-axis. And then let's say we go along and we change it by delta x, our x. So now our new point is here, a plus delta x, and if we go up to our graph, it's somewhere up here, and I'll actually extend the graph this way. So then our f of a plus delta x is up there, okay? So let's look at the tangent line, though, at a. So if we draw the tangent line, it looks something like that, okay? So here, this is actually kind of a, it's kind of a big change, but anyway, so according to this tangent line, what we have, the following triangle. So here I'm going to extend this line out, okay? So a horizontal line from this point, and I'm going to blow up this triangle right here, okay? So it'll look something like this, okay? So, well, whoa, that was supposed to be a horizontal line. There we go. So this horizontal line The length of that is given by our delta x. That's how much we changed along the x-axis. And then this here, we don't know really what that is, but we do know that the slope of this line, so the slope of this line should be, for our tangent line, m is the slope, right? And m should be equal to f prime of a, right? So we're going to take the first derivative. The first derivative gives us the slope of the tangent line at a certain point, and since this point goes down and is x equals a, then that means f prime of a, okay? So we do know m is slope, right? So slope is rise over run, so we can say that m, which equals slope, which equals f prime of a, is equal to rise over run. And we know that our run in the x direction is delta x, right? So we can say that f prime of a is equal to rise over delta x, okay? So I'll continue this again on the next slide. So if we're here, f prime of a equals rise over delta x. To solve for rise, we just multiply by delta x on both sides. So we get that rise, how much it goes up on the triangle, is equal to f prime of a times our delta x, okay? So on our triangle, again, this looks like the following. So we have our delta x on the bottom, and now we have an f prime of a times delta x as this side here, the vertical line, okay? So on our other graph, this is what it looks like. So we had something like that, and here's our a. So there's our a, here's our f of a, and then we had our a plus delta x, and that goes up and meets the graph right there. So we have something like that. So this is our f of a plus delta x, and now we draw on the tangent line to approximate, right? So something like that, and here's our triangle. Okay, so we just found that this side of our triangle, this triangle here, is f prime of a times delta x, okay? And this here is about equal to the distance or the difference in between the values of our function at the different points, right? So this is actually, if we extend those horizontal lines out, this is the full distance or the full difference, right? This is our delta f, and this is about equal to it. So that's where we get our approximation from. So delta f, the change in the function value, is about equal to f prime of a times delta x if delta x is small, okay? So here's our equation. That's how we derived it from our graph and everything. And now we can also express this in what's called differentials. That just means writing in the d's, in the letter d, to replace the delta, the triangle. So in differentials, this would look like df is about equal to df, or you could even say dy. So I'll just write that too. So or dy is about equal to f prime of a, and we're going to replace this delta with a d, so dx, okay? And yeah, so that's pretty much it. Now let's do an example of this.
Call me on my cell phone, late night when you need my love. Call me on my cell phone.